Hi everyone. Today we'll see the DC response of series RC circuit. Here DC voltage source is connected through the switch S to the series RC circuit. Here the assumption is the capacitor is initially uncharged, and when the switch S is closed in this direction, when the switch S is closed, it will get short circuit at t is equal to 0. We can determine the complete solution of the current. The current solution we can find out. So as a first step, we need to apply the KVL to this circuit. If you apply KVL to this circuit, the source voltage is equal to resistance voltage, voltage across resistance plus voltage across capacitance. V is equal to R into I. Voltage across capacitance is nothing but 1 by C integral I into dt. By differentiating on both sides, we'll get differentiation of constant voltage 0 R into di by dt plus 1 by C into differentiation of integral term will give the only I, that is I by C. I can rewrite the same equation by dividing with R on both sides, like di by dt plus 1 by RC into I is equal to 0. So this is the equation 1. The equation 1 is a linear differential equation with only the complementary solution or complementary function, because the particular solution is 0. Like in the series RL circuit we have seen, we got this k term also, but here the k term is missing, so that's why we'll get only complementary function in the solution. Anyway, we can compare the same first equation with the known differential equation like we have seen in the RL circuit. The known differential equation is dx by dt plus px is equal to k. This is the second step. You can assume compare the first equation with the known differential equation, so that you will get x is equal to I, p is equal to 1 by RC, and k is equal to 0. K is equal to 0. For the known differential equation, the solution is x of t is equal to e power minus pt integral k into e power minus pt into dt plus c into e power minus pt. By substituting these compared values, you can get the solution for this second equation, that will become like I of t is equal to, in this first term k is equal to 0 means this entire term will become 0, that's why 0 plus c into e power minus p into t. P is equal 1 by RC, that's why minus 1 by RC into t. You will get I is equal to c into e power minus 1 by RC into t. This is the third equation. So first step, we got the differential equation with this KVL equation for the given circuit diagram, then known differential equation, and with that we find the solution in the third step. But in the third equation there is an arbitrary constant c. To find out this arbitrary constant, use the initial condition. Use the initial condition to find the value of c. When the switch S is closed at t is equal to 0, since the capacitor property, like capacitor never allows a sudden change in voltage, how the inductor does not allow the sudden change in current, here capacitor do not allow the sudden change in voltage. We will use this property of the capacitor and we will find out this C value. It will act like a short circuit at t is equal to 0 plus instant also. That means whatever the voltage across capacitor earlier, that is 0 minus case or 0 case, the same will be there at t is equal to 0 plus instant also. As we have told that, we have seen C is initially uncharged and the current flowing through this C is also 0, and we will see with that initial conditions, like if you use the initial conditions at t is equal to 0 minus, in the past at t is equal to 0 minus, the switch is open. Initially the switch is open. When it is open, the voltage across capacitance in this circuit diagram, when it is open, the current flowing through this capacitance is 0 and C is also uncharged, so that the voltage across capacitance is also 0. The voltage across capacitance is 0 when switch is open, and current is also 0. But at t is equal to 0, at present we are closing the switch. When switch is closing, the same capacitance voltage will carry forward till t is equal to 0 plus, like capacitor do not allow the sudden change in voltage. That's why the same voltage 0 volts, the same 0 volts at t is equal to 0, and at t is equal to 0 plus also switch is closed, and it will give the same voltage like Vc is equal to 0 volts only. However, current if we see, When switch is closed, source voltage is directly applied to the resistance. This capacitance will get short circuit. So if you apply the Ohm's law, I is equal to V by R. That's why I is equal to V by R whenever the switch is closed. But the capacitance voltage is 0, like it will carry the same voltage from t is equal to 0 minus onwards. I is equal to V by R whenever the switch is closed, because capacitance is getting short circuit. So those are the initial conditions. Based on the initial conditions, if you see at t is equal to 0 plus, we'll substitute in the same current equation I of 0 plus, which is equal to C into e power minus t by RC, right? At t place I have substituted the 0 plus, e power 0 plus or e power 0 is nothing but 1. So I of 0 plus, like we have seen with the initial conditions, at I of t is equal to 0 plus, the current is equal to V by R. That only I am using here. So by substituting that V by R on the left side, C into e power 0, which is equal to 1. So C is equal to V by R. The same C is equal to V by R, I will substitute in the third equation. The third equation is this one, right? I is equal to C into e power minus 1 by RC into t. In that, if I substitute, I is equal to V by R into e power minus t by RC. So here I can rewrite the same equation like V by R into e power minus t by tau. This denominator RC I am considering it as time constant. If you see how the time constant, while the time constant is changing, how the response will change, that we'll see. When the switch S is closed, the response decays with time as shown in this figure. So if you see the figure, on y-axis current, on x-axis time constant I have considered. Here I have considered time constant means the same. If you replace the t with the tau, 1 tau, 2 tau, 3 tau, 4 tau, 5 tau, how this current response will decays or how this current response will change, that's what we'll observe here. If you see, the quantity RC is the time constant and it is denoted by the tau, because by replacing the t with RC, then only the power of E will become 1. That's why it is called as a time constant. So tau can be replaced with the RC seconds. So at t is equal to 1 tau, current will become V by R into e power minus 1 tau by tau, which is equal to e power minus 1. So you will get 36.8% of V by R. 36.8% of V by R. In a similar way, if you substitute t is equal to 2 tau, e power minus 2, which will give 0.135 times of VR, and so on. When t is equal to 5 tau, I is equal to V by R into e power minus 5 tau by tau, which is equal to e power minus 5, and which you will get it as 0.0067 times of VR. If you see, after 5 tau time constant, the curve reaches to 99% of its final value. What is the initial value of the current? What is the final value of the current? We can find out by using the same equation. By substituting t is equal to 0, you will get the initial value. By substituting t is equal to infinity, you will get the final value. That's what I have done here. Initial value is nothing but I of 0 is equal to V by R into e power 0, which is equal to V by R. Final value is equal to I of infinity, which is equal to V by R into e power minus infinity. E power minus infinity is nothing but 1 by infinity, which is equal to 0. That's why in the curve also, if you see, I curve, at t is equal to 0, V by R, at t tends to infinity, the curve will reach to the 0. After 5 tau, it will reach almost 99% of its final value, means 99%. It is almost close to the 0. Final value is nothing but 0, right? That's what the current response. If you know the current response, you can find out the voltage across resistance. Voltage across resistance is nothing but R into I. R into I equation is nothing but V by R into e power minus t by RC. So that I will substitute here. R and R will get cancelled. VR is equal to V into e power minus t by RC. In a similar way, we can find out the voltage across capacitance VC. VC is equal to 1 by C into integral I into dt. 1 by C into integral I is nothing but again V by R into e power minus t by RC into dt. If I integrate this V by R is constant, that I will take it out of this integration. So V by RC, if I do the integration of this e power minus t by RC, e power minus t by RC by the coefficient of this t term will come as a denominator, that is minus 1 by RC plus initial value as C. So to find out this C value, again I'll use the initial condition. Here if you see RC will get cancelled, minus V into e power minus t by RC plus C. If I use the initial condition, like I told during the initial condition, at t is equal to 0, the voltage across capacitance is 0. By substituting t is equal to 0 in this equation, Vc is equal to 0, you will get the minus V into e power 0 plus C. C is equal to C minus V is equal to 0, which is equal to C is equal to V. So by substituting this C is equal to V in this equation, let us assume this as fourth equation. In fourth equation, you will get Vc is equal to minus V into e power minus t by Rc plus C is equal to V. If I take V common, V of 1 minus e power minus t by Rc is nothing but voltage across capacitance. As we know the voltage across resistance equation and voltage across capacitance equation, I can draw those waveforms also. On y-axis, I'll take the voltage, on x-axis time constant. If you see the voltage across resistance, it is decaying function. That's why at t is equal to 0, V voltage at t tends to infinity, this term will become 0. That means VR will become 0, decaying function. So initially V, and it will go close to the 0. That's what voltage across resistance. If you see voltage across capacitance, 1 minus of the decaying function, that means, or V minus of V into e power minus t by RC. E power minus t by RC is nothing but VR. From this dotted line, if you subtract this VR line, you will get the Vc. So by subtracting V minus 0, so V minus V, then V minus, slowly the magnitude is reducing, so here magnitude will increase and it will reach to the steady state after 5 tau time constant, like 1 minus e power minus x curve. Okay, so the power in, next we'll find out the powers in resistor and capacitor. Power in resistor is nothing but voltage across resistance into current. Voltage across resistance is nothing but V into, voltage across resistance is nothing but V into e power minus t by RC into voltage into current is nothing but V by R into e power minus t by RC. By multiplying this, V square by R into, both bases are same, powers will be added, e power minus 2t by RC. In a similar way, power in capacitor is nothing but voltage across capacitance into current. Voltage across capacitance is nothing but V of 1 minus e power minus t by RC into current is nothing but V by R into e power minus t by RC. By multiplying these two, V square by R into 1 into e power minus t by RC, which is equal to e power minus t by RC minus e power minus 2t by RC. As bases are same, powers will be added. Again, I can draw the equation for this power curve and power in resistance and power in capacitance. So power on y-axis, time constant on x-axis. So steady state power is nothing but V square by R, the dotted line. If you see the power in resistor, voltage in across resistor into current. Voltage across resistance is decaying function, and voltage across resistance is decaying function, current is increasing function. So voltage across resistance is decaying function, and current also it is decaying function. So power in resistor also you will get it as a decaying function. However, if you see the capacitance, power in capacitance, voltage across capacitance is increasing function, 1 minus e power minus x means that is increasing function, whereas current is decaying function, it is just like e power minus x term. So one is decaying function, another one is increasing function. So the power will increase then decrease, or just directly in both the equations, power across resistance, power in resistor and power in capacitance, in both the equations you can substitute t is equal to 0, t is equal to infinity, then you will get the same power equation. When t is equal to 0, 1 minus e power 0, 1 minus 1, which is equal to 0. When t is equal to infinity also, e power minus infinity is nothing but 1 by infinity, which is equal to 0. Here also 1 by infinity is 0. Pc is equal to 0 only, like that. So this is all about the DC response in series RC circuit, and based on this we'll do the problem. If you see the problem, a series RC circuit consisting of resistor of 10 ohms and capacitor of 0.1 farad as shown in figure. A constant voltage of 20 volts is applied to the circuit at t is equal to 0. Obtain the current equation, determine the voltages across the resistor and capacitor. This is the circuit diagram, given circuit diagram. 20 volts through the switch S is connected to the 10 ohms resistance and capacitance of 0.1 farad, and the current response we need to find out. As a first step, what we have to find out, we have to apply the KVL to this circuit. If you apply KVL, 10 into I plus 1 by C, which is nothing but 1 by 0.1 into integral I dt is equal to voltage, source voltage, that is 20 volts. By differentiating on both sides, the equation will become 10 into di by dt plus differentiation of integration will give only I by 0.1 is equal, differentiation of 20 is nothing but 0. By rewriting this equation, di by dt plus I is equal to 0 by dividing this equation on both sides with 10. That is your first step, that is nothing but first equation. The non-differential equation is nothing but dx by dt plus px is equal to k. By comparing this first equation and second equation, you will get x is equal to I, p is equal to 1, p is equal to 1, k is equal to 0. By substituting these terms in the non-differential equation solution, like x of t is equal to e power minus pt integral k into e power plus pt into dt plus c into e power minus pt, you will get the I of t is equal, because k term is equal to 0, that's why first term will be 0, only second term will be there, c into e power minus p into t, p is equal to 1, that is nothing but e power minus t. I is equal to c into e power minus t is nothing but third equation. Use the initial conditions and find out the C value. At t is equal to 0 minus, switch is open, voltage across capacitance is 0 and current is also 0. When t is equal to 0, switch is closed. Capacitance do not allow the sudden change in voltage, that's why the same voltage 0 volts. But however, if you see the current is nothing but, again, when switch is closed, short circuit, resistance and capacitance is getting short circuit. So voltage and resistance in a loop, the current is nothing but I is equal to V by R. That's why I is equal to V by R. Even at t is equal to 0 plus also, the switch is closed, the same voltage will be there, because capacitor do not allow the sudden change in voltage, and current is also I is equal to V by R. By substituting these initial conditions, you will get I is equal to, for example, if you see at t is equal to 0, what is I value? I is equal to 20 by 10, which is equal to 2 amperes. This 2 amperes are substituted in this equation at t is equal to 0 plus, I of 0 plus is equal to c into e power minus t, that is nothing but 0 plus, I of 0 is nothing but 2 amperes, c into e power 0, so which is equal to c is equal to 2. By substituting the same equation, I is equal to c into e power minus t, c is nothing but 2 into e power minus t. And if I want to get the voltage across resistance is nothing but R into I. R is equal to 10 ohms into I equation is nothing but 2 into e power minus t, which is nothing but 20 into e power minus t volts. And voltage across capacitance Vc is equal to 1 by c integral I into dt. I will substitute this I equation, 2 into e power minus t in this equation, 1 by c is equal to 0.1 integral 2 into e power minus t into dt. By integrating this, 2 is constant, that I will take it out of that integration, 2 by 0.1, integration of minus t is nothing but integration of minus t by minus 1 plus c, that initial value. Then if I do the integration, 2 by 0.1 which is equal to 20 minus 20 e power minus t plus c. To find out this c value, use the, again at t is equal to 0, the voltage across capacitance is equal to 0, right, initial condition. By doing that, Vc is equal to 0 minus 20 into e power 0 plus c. From this we will get c is equal to 20. By substituting that c is equal to 20 in this equation, Vc is equal to minus 20 into e power minus t plus 20, which is equal to Vc is equal to 20 of 1 minus e power minus t volts. So this is all about the problem based on the DC response for series RC circuit. Thank you all.